Hello everyone! In the video today, we're going to talk about the rate in, rate out free response question. We can do a quick summary, breakdown of the questions, how to answer the common questions, and then I think 3 full free response question examples. Okay, let's look at the breakdown, the question types. Most of it is finding the total amount in or out of the system. Then we can apply the total amount. That might be something like the ticket prices are, I think we're going to see that later. The ticket prices are $11 from 9 o'clock to 5 o'clock, and then after 5 it's cheaper. It's like $11. Then there's finding the absolute min or max, increasing or decreasing, and average value or explain in context of the problem. But let's get to the crux of the matter. The big idea here is that to get a total amount, we integrate the rate. So we're typically given a rate in, the location, and then the rate out. So some examples, I'm going to use the word population and location for rate in, rate out problems. We could have oil in a tank, where oil is the population, or like the thing that we're asking about, and the location is the tank. It's either being filled into the tank, or maybe there's a hole at the bottom of the tank and it's leaking out. That would be the rate out. We had air in a balloon, people at a carnival, cookies bought at a supermarket, tourists at the Statue of Liberty. These are all examples of rate in, rate out, where we're looking at a location and we're given 2 rates, the rate of people coming into the location, the rate of the population coming out of the location. So they'll almost every single time they'll ask how many people entered in this time interval, or how many people exited in this time interval, or how many people are in the location between these 2 time intervals. So the total population entering, well, our big idea is to integrate the rate to get the total amount. So all we have to do is integrate the rate they give us that describes the rate in the interval they ask us, from A to B. Likewise, for the total population leaving or coming out, we just have to integrate the rate out from A to B. Then, if we want to know the rate of change of the population in the location, then we need to, I think the easiest thing is to think about an example first. So let's say the rate in is 5 people. So 5 people per minute are coming into the location, and the rate out is 3 people per minute. So every minute, on average, 5 people come in, 3 people go out. So then what is the rate of change in the location itself? Well, this is kind of an intuitive problem. It would be 2 people per minute. If 5 people are coming in, but then 3 people leave, then there's really only like 2 people are coming in to the location each minute. And that's given by the rate in minus the rate out. And if we want the total population in, well, again, we're applying this big idea that to get the total amount, we integrate the rates. So we're going to do the initial population. They usually give us an initial value, plus the integral from A to B of the difference, rate in minus rate out. We're going to get a lot of practice with these formulas. Another very common question is to say, is the number of people in the location increasing or decreasing? Well, if the rate in is bigger than the rate out, then the number of people would be increasing. The total amount in the location is increasing. And if rate in is smaller than the rate out, you get -4 people. People are leaving faster than they're coming in. Then the number of people, the total amount in the location is decreasing. So we're going to consider rate in minus rate out and whether it's positive or negative. So if you subtract the 2 rates and you get rate in minus rate out as positive, it means that the total amount is increasing, and if it's negative, it's decreasing. Min-max is also a very common one. What is the minimum or maximum of the population in the location? So at what time of day is there the most amount of people at the Statue of Liberty? That's like a common question. So the total population is from the previous example, is the initial population plus the integral of rate in minus rate out. And if we take the derivative, now we're applying a fundamental theorem of calculus. Well, the initial population is just a constant, so that'll be 0. And then when we take the derivative of this, we'll just get rate in minus rate out. And we know if we're finding min-max, we take the derivative, set it equal to 0. Now we get rate in minus rate out equals 0. That means we can set them equal, see where they're equal using the calculator. That's like with the intersection point. Find the intersection point between them. That's the basic idea of finding the min and max. And of course, we still have to test with the number line. And if it's absolute min or max, then we need to include the endpoints. Whoa, that is bright. So this is a problem. This is the type of problem that students look at once and then say, I don't want to do calculus anymore because it's so much. It looks like it's a lot. But we're going to break it down. So we have the rate at which people enter an amusement park on a given day is modeled by the function e. We got our rate in. The rate at which people leave the same amusement park on the same day is modeled by the function L. It's our rate out. Both E and T are measured in people per hour, and time T is measured in hours after midnight. These functions are valid for 9 to 23, the hours during which the park is open. At time 9, there are no people in the park, which makes sense, and it is an initial condition. Alright, part A. How many people have entered the park by 5 p.m., which really means that T is 17. And round our answer to the nearest whole number. Okay, so we got people as our population, and amusement park is the location. And we want to know how many people have entered the park. Okay, for total in, we're just going to integrate the rate that they give us for entering. And they say it begins at 9, so our bottom bound is 9. And they tell us at 5 o'clock, which means T is 17. So if we put this in the calculator, we do our math 9. Then we put the bounds in, 9 to 17. And the function, we should get 6004.270, but since we're rounding to the nearest whole number, it would be rounding down. 6,004 people entered the park by 5 p.m. And I'm just showing like what the screen of the calculator. You need to let me know if you don't know how to do this in class. But we put it in the calculator and we get same number, 6004.270. We get 3 points for this. We get 1 point for the limits, 1 for the integrand, and 1 for the answer. So you can write, this is exactly what is expected of you. You don't actually have to write the whole thing out on your paper. You just need to write E of T. But you do need to do it in the calculator, so. But that's not so bad. They ask us how many people entered the park. We have the rate at which people enter. We apply the big idea. To get the total amount, we integrate the rate. Okay, part B. The price of admission to the park is $15 until 5 p.m. After 5 p.m., the price of admission to the park is $11. How many dollars are collected from admissions to the park on the given day? And round your answer to the nearest whole number. Okay, so let's simplify this a little bit. Let's say it's $15 and 3 people enter. Then how much money did you make? You made $45 because 3 times 15 is 45. So multiplication is key here. If we know how many people entered the park by 5 p.m., then we can multiply that by 15. And then if we know how many people entered the park after 5 o'clock, we can multiply that by 11 to get the total amount from each of those sections. So we're going to find the total number of people entering in each time interval and then multiply by the price of the ticket. So the first part, between 9 and 17, it's the same integral we had in part A, except we're multiplying it by 15, which is the price of each ticket. Then we're adding to that the $11 per ticket times the number of people that enter the park after 5 o'clock, which would be starting at 17 and ending at the end of our interval, 23. And we can put it in the calculator. Let's see this play out. Plus 160 dx plus 11 math 9 17 to 17 to 23, and then we got to do this whole function again. But the big idea I want you to take away from this is the multiplying part, that we just split this into 2 time intervals, before 5 o'clock and after 5 o'clock. Then we multiply the amount of money, the price per ticket by the number of people entering, and then the price per ticket, the number of people entering. And we get $104,048. This is the work that they show, and this is 1 point. It's kind of a bummer, but it is only 1 point. The good news is that it's only for the setup. They don't even really care about the number for some reason. So if you write this like we had on the other page, don't go crazy about the actual calculation. Again, the most points you get in this test are from the setup and not from the final answer. Okay, C. Let h of t equal the integral from 9 to t of e to the x minus L of x. Notice that that's rate in minus rate out for 9 to 23. The value of h of 17 to the nearest whole number is 3,725. Find the value of h prime of 17 and explain the meaning of h of 17 and h prime of 17 in the context of the park. Okay. By the fundamental theorem of calculus, the derivative of h, well, the derivative would cancel out here, and we put the t inside. We just get e of t minus L of t. And if we plug in 17, it would be e of 17 minus e of L of 17. And what I did here is I graphed both of them. I put them in y1 and y2. Here's what it looks like, y1 and y2. And if you look at the table, it's just another way of doing it. You can, of course, just plug in. That's fine. But I went to the table, and then you can take these two values at 17 and subtract those. And when you do that, you'll get negative 380.281. So the explanation here is the meaning of h of 17. Remember, rate in minus rate out would be when we integrate that is the number of people in the location, the number of the population in the location. So there were 3,725 people in the park when t is equal to 17. Then the number of people in the park was decreasing at the rate of approximately 380 people per hour at the time t equals 17. So remember, h prime is the derivative. If the derivative is negative, it means the original function is decreasing. So the number of people is decreasing at a rate of 380. And notice that we have units here. Units is very important. And that when we say we're decreasing, we don't include the negative sign. That's like a little tiny thing that might lose you a point. That if we say we're decreasing and it's a negative, you don't include the negative in your explanation. And we get 1 for the value of h prime of 17 and 2 for the meanings of h of 17 and h prime of 17. But we get minus 1 point if we don't reference t equals 17 at all. That's kind of hard to do in this problem. Alright, D. At what time between 9 and 23 does the model predict that the number of people in the park is at a maximum? Alright, we know max means take the derivative and set it equal to 0. And we just figured out that the derivative of h prime is also, h prime of t is equal to e of t minus L of t, rate in minus rate out. So it's where the rate in and the rate out are equal. And we can use the calculator to find the intersection points. And we get 15.794 or 795. And again, we just do y equals, set them equal. Another way we could do this is to just use this instead, e minus L, as one function and find the zeros. But anyway, this is a quick one. We get 2 points, 1 for the subtraction, setting it equal to 0, setting the derivative equal to 0, and 1 for the answer. And we finished one. Give someone a high five. Alright, let's go. Question 2. A tank contains 125 gallons of heating oil at time 0. During the time interval 0 to 12, heating oil is pumped into the tank at the rate blah 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 gallons per hour. During the same time interval, heating oil is removed from the tank at the rate blah 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 gallons per hour. Alright, so we got our tank. When we say tank, it's like something that holds something else, like a container, not like a tank, an army tank. Container, not an army tank. So the tank is our location. The heating oil is the population. And we have an initial condition at time 0. We have 125 gallons of oil. Then we have our rate in, our rate out. We are ready to start answering some questions. Part A, how many gallons of heating oil are pumped into the tank during the time interval 0 to 12? How many? How many? If we want to know how many, we integrate the rate. And we are going into the tank, so we're going to use our function for rate in. So they give us the bounds too, really nice. The integral from 0 to 12 of h of t. We can plug in the function, and we get, if we put it in the calculator, let's see, we get 70.570 or 571. And that's it. That's a quick 2 points. One for the integral, one for the answer. This is a very friendly question, and it's really good to get those 2 points right away. Part B. Is the level of heating oil in the tank rising or falling at time t equals 6 hours? Give a reason for your answer. Okay, so rising or falling, that would mean the amount of oil inside is increasing or decreasing. So we can take the difference between h of t and r of t, right? If we want to know increasing or decreasing, we do rate in minus rate out. So we do rate in at 6 minus rate out at 6, and we end up getting negative 2.924. And just to show that work in the calculator, I plugged in 6 for h of t, then we can plug it in for r of t, and what do we get? By the way, make sure you're in radian mode, because you'll get all the wrong answers and you'll be very sad. Negative 2.924. Got it, same thing. And so we can say, since it's negative, it is falling. And one thing we need to remember when we're writing our reasons, our justifications for these problems, is that we need to include the math, then we need to include what we're talking about, like the population. We need to say the level of heating oil is falling, and we need to include the time every time. When they tell us at t equals 6, we also in our answer have to say at t equals 6. This is 1 point for the answer with the reason. Part C, how many gallons of heating oil are in the tank at time t equals 12 hours? All right, this is good. How many gallons are in the tank at time equals 12? So remember that the tank is the location, so that means we're going to integrate rate in minus rate out. And we need to remember the initial value. So it'll be the initial value, 125, plus the integral from 0 to 12 of rate in minus rate out. And we can show this. I do have the 125 over there somewhere. We will get, eventually, 122.025 or 026, depending on whether you truncate or round. And again, when you're writing your work on the paper, you don't need to write out the whole functions. You can just write h of t minus r of t. But don't forget that initial value is important. On the calculator, do we get the same answer? We do. And again, radian mode is important here. We get 3 points for this. 1 for the limits, 1 for the integrand, which is the inside, and 1 for the answer. Part D, at what time t between 0 and 12 is the volume of the heating oil in the tank the least? Show the analysis that leads to your conclusion. Okay. So the least means the absolute minimum. And when we have an absolute minimum, we need to check critical points and endpoints. And so just like before, we're going to have h of t minus r of t is 0, which means h of t is equal to r of t. And we got a whole lot of stuff going on here. So I'm finding the two intersection points here using the second calc business. And we get our two intersection points to be 4.790, that one, and 11.318. So I graphed the rate in, graphed the rate out, find where they intersect. That's the solutions for this equation. Now, once we know the intersection points, those are like our critical points that we're going to check. So we have these two critical points that we just found by setting the derivative equal to 0. Then we got our endpoints, 0 and 12. And now we're going to look at the graph. So this is the graph of h of t minus r of t when you put all of this minus all of this in the calculator for y1. So if you look between 0 and 4.79 and between 11.38 and 12, it's above the x-axis, which means it's positive. Then between 4.79 and 11.3, it is below the x-axis, which is negative. And let's do the increasing, decreasing part. That's good. So the volume increases until 4.79, then decreases until 11.318, then increases again. And that means the absolute minimum has to be either at 0 or at this relative minimum, 11.318. So let's test both of those. Well, we know what it is at 0. At 0, it's 125. That's the initial condition. So we have to test out 11.318 and get the actual value. So we do that with the integral. We plug it in, the same pattern we're seeing of the initial value plus the integral of rate in minus rate out from 0 to 11.318, and we get 120.738. And so since the volume is 125 at t equals 0, the volume is least at 11.318 because it's less than 125. How many points we get for this? 3. And good, because we did a lot of work for it. So we get 1 point for setting rate in minus rate out equals 0. And that's going to happen every time we're trying to find a min or max. Set h of t rate in minus rate out equals 0. Then we get 1 point for saying it's least at 11.318, and then 1 for the analysis. High five another person. We did 2. All right, let's go. High five a raccoon or something. Don't high five a raccoon. That is not a good idea. They're dangerous, even though they look adorable. All right, this is the last one we're going to do. 4. Time between 0 and 31. The rate of change of the number of mosquitoes on a tropical island at time t days is modeled by blah 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 mosquitoes per day. There are 1,000 mosquitoes on the tropical island at time 0. All right, so the number of mosquitoes is our population, and the tropical island is our location. We have a rate, but this one is, a little bit different. It's neither a rate in nor a rate out. It's the rate of change of the number. So it's the same as rate in minus rate out. We just don't have those two functions. Instead, we combine them into just this one. So again, this rate of change is the rate of change of the number of mosquitoes on the island, which before is what we were saying was rate in minus rate out. And our initial value, 1,000 mosquitoes at the beginning. So show that the number of mosquitoes is increasing at time 6. Well, if r of t represents the rate of change of the number of mosquitoes, then we just need to show that the rate of change is positive. If the rate of change is positive, it means that the number of mosquitoes is increasing. That makes sense. If it was negative, it means mosquitoes are dying and it would be decreasing. So we plug in 6, making sure we are in radian mode, and we get 4.438, which is greater than 0. And we get 1 point for this. I'm happy with the 1 point. It was a quick one. We just had to evaluate a function. That's nice. 1 point. Quick and easy. At time 6, is the number of mosquitoes increasing at an increasing rate, or is the number of mosquitoes increasing at a decreasing rate? Give a reason for your answer. Okay, so this is a kind of a strange problem. Increasing at an increasing rate. If you're increasing at an increasing rate, it means you're concave up. That's another way of saying concave up. If you're increasing at a decreasing rate, it's another way of saying concave down. So, since this is the rate of change, and we want to look at the rate of change of the rate of change, we take the derivative of the rate of change. So we're looking at r prime of 6, and we're seeing what it's equal to. So I did this with the calculator, actually. We can do d dx of our function, 5 square root of x cosine of x over 5, making sure to be in radian mode, and we can plug in 6. So a common mistake for students here would be to try to actually take the derivative here using product rule and chain rule, but you can do it. I have faith that you can do it, but it would just waste a lot of time when we can just put it in the calculator and get it real quick. This would take you maybe 30 seconds to put in the calculator. And we get r prime is negative 1.913, so the number of mosquitoes is increasing at a decreasing rate at time 6, which means it's concave down. So again, just to reiterate this problem again, if we want to know whether something is increasing at an increasing or decreasing rate, we can look at the derivative, or it's really the second derivative, but since this is a rate, it's the first derivative of another function. So you take the second derivative, or we took the derivative of the rate, we saw that it's negative, that means it's increasing at a decreasing rate, which means the original, a function that would describe the total amount of mosquitoes on the tropical island would be concave down. So there's 2 points. We get 1 for considering r prime of 6, and 1 for our answer with the reason. Part C, according to the model, how many mosquitoes will be on the island at time equals 31? Round your answer to the nearest whole number. So the total amount is the integral of our rate with the initial condition. So 1,000 plus the integral from 0 to 31 of the rate. We put this in the calculator. We should get, to the nearest whole number, there are 964 mosquitoes. So we're going to end up rounding down here. I put it in the calculator and hit enter. We will get 964 point something. Come on, calculator, let's go. 964.335. Okay, so we're rounding down. And we get 2 points. 1 for the integral, 1 for the answer. All right, last part. To the nearest whole number. What is the maximum number of mosquitoes for 0 to 31? Show the analysis that leads to your conclusion. Okay, remember, in the other problem, we said for any maximum or minimum, we're going to take the rate in minus rate out and set it equal to 0. But we don't have a rate in minus rate out. Instead, we have this function, which is really the same. So we're setting that rate equal to 0. And I made these different colors because they're 2 functions that when we multiply them, they get 0. So we can set each of them independently equal to 0. The first one is just going to give us t equals 0 as a solution. These other, for cosine of t over 5, we have to do a little bit more work. So remember, from your unit circle, that cosine of pi over 2 is 0 and cosine of 3 pi over 2 is 0. So we can set up this equation. The insides should be the same. So pi over 2 is equal to t over 5. That would give us, if we multiply, t equals 5 over 2 pi. Same thing with 3 pi over 2 equals t over 5. Multiply by the 5, we get 15 over 2 pi. So on a number line, we have our 5 halves pi and our 15 halves pi. Then we have our endpoints, 0 and 31. And this is the graph of r of t. So if we look at the graph, between 0 and 5 over 2 pi, we are above the x-axis, so it's positive. Then between 5 over 2 pi and 15 over 2 pi, we are negative. And between 15 over 2 pi and 31, we are positive again. And note that I changed the window here. You're going to end up having to change the window pretty much every time for these problems. But the good news is it's easy to figure out what. I put my x min to 0 and my x max to 31, and then I had to play around a little bit with the y min and y max. Then we're increasing, decreasing, increasing, just to show that. Now, the maximum either occurs at 5 over 2 pi, because we have a relative maximum there, or at the endpoint 31, because we don't know how far it increases here. So let's plug it in for pi. They did 2.5 pi instead of 5/2 pi, but it's the same. If we do that, we'll get a total amount of 1039.357. And from part C, we already found that. We got 964. So we just take the one that's bigger, and we make our conclusion. There are 964 mosquitoes at time 31, so the maximum number of mosquitoes is 1039 to the nearest whole number. And that's at time 31. Sorry, that's at time 5/2 pi. Whew. We get 4 points for this one. 2 for the absolute maximum value, which includes the integral and the answer. And then 2 for the analysis. So the critical points on the inside, getting these two, 5/2 and 15/2 pi, we get a point for that. And for completing the analysis. All right. Give someone a high five and take a break. We are definitely going to do more practice with these during the week, but I hope this was a helpful breakdown of what these questions are like, and you'll be a little bit more comfortable with them when we go over them together. Okay, see you in the next video.